in the 11th grade, you studied about the electric field when a charged particle, for example, if you rub a balloon with your hair or with some woolen cloth, this balloon gains electron from the woolen cloth, and after that, this charged balloon produces electric field. We say this is electrostatic. This part is electrostatic. So because electrons from the woolen cloth, resides on the surface of this balloon, and then when they reside, they stay at rest. They don't move. Statics. That's why it's coming this name, electrostatics. This is the phenomenon which is the charges are not in motion. They are resides on the surface of a material and then produces an electric field around this material. So if you rub your comb with your hair, and also the same thing happens. And if you touch this comb with the pieces of paper, you are going to see that this comb attracts the paper. So that title was given as electrostatic, and that field produced around the charged particles was called electric field. In the 12th grade now, we are going to talk about the magnetic fields. Basically, field concept. Why do we need field? Why field concept is needed to explain the physical phenomena? Remember, in physics, we have two types of forces, or objects interact with one another by two ways. One of them is objects get in contact. You can hold an object with your hand and the object is in contact, and you can push and pull that object. This is contact. So forces can be divided into two groups. One of them is the contact forces. So for contact forces, an interaction between the objects is not so difficult to explain. They are in contact, so pushing and pulling, we see that. However, it is also possible to see the interaction between the particles without contact. These forces, if two objects are interacting with one another without contact, which are called non-contact forces. So how do they communicate? How these two objects communicate with one another? So we explain this communication by field. Field concept is produced or they're established to explain the interaction between two non-contact objects. So non-contact forces are also, that's why named as field forces. There are three basic non-contact forces we will learn now. One of them, in fact, two of them you learned already. One of them is the gravitational field or gravitational force. For example, remember in section 1, chapter 3, we talk about that. Earth and moon attracts one another. Is there a connection between them? Is there a contact between them? No. How do we explain this interaction between the Earth and moon? So we say that, Earth produces a gravitational field around, remember, G, and moon produces a gravitational field around itself. So these two gravitational fields interact with one another, so then they attract one another. We explain it like this, gravitational field. Second one is, you studied last year, electric charges, electrons and protons. For example, electron and proton. Are they in contact now? No. How do they interact? How do they pull each other, attract each other? How can we explain this? Then we explain like that. Yes, every charged particle produces an electric field around itself. When another particle, a charged particle, enters inside this electric field, it will be attracted. So electric field is used to explain the interaction between charged particles. Same thing can be done by magnetic field. Okay, when you keep a magnet closer to an iron, you are going to observe that, this magnet is attracting iron. Why? How can we explain that? So we say that, yes, this magnet produces around itself a field. That field is known as a magnetic field. So magnetic field is the field produced around a magnet. Electric field is the field produced around a charge. But electric field, as I said in the 11th grade, you learned, produced by the electric charges which are at rest. This is the key. Yani, if some charge resides on the surface of a material, around this material there will be formed electric field. Electric field is due to the electric charges which are at rest. However, magnetic field is not like this. Magnetic field is produced by electric charge, again by electric charges. Yeah, electric field is produced by electric charges. Magnetic field is produced by electric charges. But in electric field, charges are at rest. But in magnetic field, those charges must be in motion. So if a charge moves in one direction, moves somehow, so this charge will produce a magnetic field. Now I will go with detail. So we are going to look first the atom. You know the structure of an atom. There are nucleus of the atom, which is nucleus. And nucleus of the atom consists of positively charged particles and neutrons, which are not charged. And this is the nucleus, and electrons are revolving around the nucleus. So these electrons are revolving around the nucleus. And then these electrons are moving with some tangential speed, even one with some angular speed. These electrons are in motion. So if these electrons are in motion, then you can say that yes, these electrons, because we know that charge in motion produce a magnetic field, these moving electrons can also produce a magnetic field. So inside an electron, inside an atom, electrons are in motion. Origin of this magnetic field, all this magnetic field is because of the motion of the electrons inside an atom, which are revolving around the nucleus. Electrons are in motion in an atom. This origin of the magnetic field is this. Yani electrons are moving inside an atom. So this motion produces all these magnetic field lines around the magnet. So I will go with details about this now. So electrons inside an atom exhibit two types of motion. One of them is electrons are revolving around the nucleus of the atom, just like planets are revolving around the sun. We are going to study, if we can, in chapter 8 about this. Electrons are revolving around the nucleus of the atom. This motion, as they are revolving around the nucleus, so then they are charges in motion. So this motion of electrons provides a magnetic field to an atom. One part is this. Second one, these electrons are at the same time rotating, spinning about their own axis. This rotation about their own axis also provides a magnetic field to the atom. For that reason, because of these two motions, one of them is the electrons are revolving around the nucleus. Second one is electrons are spinning about their own axis. These two motion makes an atom or provides an atom a magnetic field. Basically, for simplicity, these two types of motion of the electrons provide a magnetic field for each atom. So that's why most atoms behave like a very tiny magnets with N pole and S pole. Think this is atom. This shape is representing model of an atom, and so because of the motion of the electrons charges inside this atom will have an N pole and will have an S pole. So this arrow will show, yes, the direction of the magnetic field inside this atom. So every atom, not every atom, most of the atoms, why I say most you will understand later, I will explain it, but most atoms behaves like a very tiny magnet with N pole and S pole because of the two motions of the electrons. One motion is electrons are revolving around the nucleus, just like planets are revolving around the sun. Second one is electrons are spinning about their own axis, and just like the planets are spinning or rotating about their own axis. That's why most atoms behaves like a very tiny magnets with N pole and S pole. Okay, there are billions of atoms, of course. This is just for one atom. Now a new definition, domain. I will define a domain to you. What is the domain? So there are, as I said, billions of atoms which is inside this material. Groups of atoms whose magnetic fields are parallel called a domain. So I draw here a model. 3 atoms I draw. Of course, not 3 atoms inside material, but I draw 3 atoms. 1, 2, 3. As you see, their magnetic fields are parallel. So this is called a domain. Yani groups of atoms. This can be, of course, thousands, maybe 10,000, maybe 100,000 atoms, maybe billions of atoms. All they have a magnetic field in the same direction. So this is called a domain. But domains, there can be another domain because direction of the maybe other atoms have a direction of magnetic field like that. This is a second domain. As you see, they are also parallel to each other. This model also parallel. Or a third model. Okay, maybe some other groups have such a magnetic field like that. But again, they are parallel to each other. A third domain. So that's why there can be also billions of domains made of these atoms whose magnetic fields are in the same direction. So domain is that group of atoms whose magnetic fields are parallel, one domain, second domain, third domain, fourth domain, fifth domain. So basically we can say that atoms are, like good, some students are good friends if their characteristics are very, they close to each other, they like each other, and they becomes friends. Atoms are also like this. If two atoms has a magnetic field in the same, so they becomes good friends and forms a domain, a group. Other two or millions of atoms, if their magnetic fields are in, they becomes another group. Third domain, another group. So, but all they have, the magnetic fields were in the same direction. Groups of atoms whose magnetic fields are called parallel is called domains. So inside a material, there are also billions of domains. So these domains determine everything. So now another model I will show you. Here, each part is representing a domain. This is one domain. As you see, magnetic fields are in the same direction. A second domain, third domain, fourth domain. As you see, these domains are all in the same direction. Magnetic field of these domains are in the same direction. If most of the domains in a substance are in the same direction, that substance is a natural magnet. Yani this substance as a whole is a magnet. Like this one, I have my own magnet in my hand. Most of these domains are in the same direction, just like this. So that's why it becomes a magnet, if the domains are in the same direction. So this substance becomes a natural magnet, which is in my hand. But all the substances are not like this. So second one is this one. As you see, domains are in random directions like this. C domains of the one group is in this direction, another group like direction. So then domains are in random directions. If domains are in random direction, as a result, these domains cancel out each other. That's why there will be no magnetic field. So substance whose domains are in random directions, they cancel each other. The magnetic fields of domains cancel each other. That's why net magnetic field becomes zero. It's a magnetic material, just like this pin. So, or iron. Now I have an iron in my hand. This is iron. So it is, when I hold it close to something, it's not attracting because domains of this iron are in random directions. They cancel each other, and that's why net magnetic field becomes zero. Third group is non-magnetic materials. In here, no domains, as you see, just individual atoms. You see that? But these individual atoms, whose magnetic fields are in random direction, again cancel each other, but there are no domains. So this is the non-magnetic material, like paper. Paper is a non-magnetic material. It never attracts something. Even it cannot be magnetized. Or plastic, or rubber, or this, what is this called? A bowling ball, or this billiard ball. So all these are non-magnetic materials because they have no domains. So third group. So according to the domains, if an object has or not, we can classify the substance into two groups. One of them is if the domains are in the same direction, if most of the domains are in the same direction, so substance is a natural magnet. So because they have a net magnetic field, a resultant magnetic field. Second one is if the domains are in the opposite direction, random directions, they cancel out each other, net magnetic field becomes zero. It is just like iron, which is in my hand. It's an iron, so it's not a magnet. Third one is no domains, but Atoms are domains of each atom is in random direction, so they don't. This is the paper or plastic or other things. Non-magnetic materials. They are three materials I explained according to the direction of domains or if domain exists or not. All right. Next step. Then, okay, we learned now. So this iron has domains, but these domains are in random direction. So this iron cannot attract anything. I have pins on my hand. You see this pin and another pin I have.
Yes.
These pins are iron, so they do not attract each other when I touch them because their domains are in random directions. However, now I will do something. When a magnetic material, yani iron, is a magnetic material. Magnetic material by the time doesn't mean that a magnet, okay? Magnetic material doesn't mean a magnet. Magnetic material is iron, cobalt, nickel, which can be magnetized. Now I will magnetize this by iron. When a magnetic material such as an iron exposed to a natural magnet, I have a natural magnet in my hand. I have a pin in my hand. Now I will expose this pin to a natural magnet. Now this pin will attract another pin. Now watch it. So I am going to bring another pin. You see that? So these two pins attract each other. Why? Initially they didn't, but when I expose this pin to a natural magnet, this pin becomes a magnet. It magnetized. Reason is this. Now, remember, I told you that normally magnetic materials, which is iron, has domains in random directions. However, when you expose this iron to a magnet, these randomly directed domains becomes aligned in the same direction. You see the directions? All they becomes
Yes.
the same direction. That's why there will be a net magnetic field in here, a net magnetic field. So this pin becomes a magnet and then starting to attract another pin. So this is how we can magnetize a magnetic material. So irons are very important in also industry. You can make a iron magnet and you can lift the things from the very heavy things from the ground to a ship or from ground to somewhere. You can carry them. So that's basically what's happening in here is this. So normally this pin has no domains in the same direction. All are in random directions. They are. But when I expose this pin to a natural magnet, the domains of this pin becomes in the same direction and pin starts to attracting another pin. However, one more thing. When I cut the connection, if I remove this pin, if I remove this magnet, sorry, you will see something surprising. Now I will remove this magnet. Oh my God, pin is attracting pin. This is, at the beginning it was not possible, but now it's attracting. Why? Because the domains are in the same direction, some of the domains. Still this pin can keep its magnetism for some time. But it doesn't look so long, maybe 1 hour, maybe 2 hours, maybe 10 minutes, depending on the quality of your material. So this pin can trade just like a magnet. This phenomenon is known as hysteresis. Magnetic hysteresis. Look at the definition. When external magnetic field is removed, yes, I removed the magnet, and material retains means keeps, retains its magnetization for some time. This event you observe now, pin attracts pin. This event is known as magnetic hysteresis, and this is a ministry exam question. This definition is a ministry exam question. As I said, this pin can keep other pin for maybe 10 minutes, maybe 20 minutes, maybe 1 hour, maybe 2 hours, but at the end, this pin will lose its magnetism because it's a magnetic material. Magnetic material can never be a permanent magnet, even if you don't expose them to an external magnetic field. With a sectional question, this question is also a ministry exam question. When a bar magnet is broken into two pieces, how many pulses would each piece have? Okay, remember there are domains. So in here there are domains. In fact, N pole and S pole is because of the domains, because every atom has N pole and S pole. Every domain has N pole and S pole. That's why every magnet has N pole and S pole. When you break this magnet into two, it doesn't make difference because there are still domains. And every domain again N pole and S pole. That's why how many times you divide or break a magnet into pieces, it's no matter. Each piece will have N pole and an S pole. So first piece will have N pole and S pole, second piece will have again N pole and S pole. Only thing in here happens is this. So assume that initially before breaking them, there are, I'm just giving random number, 100 domains in the same direction. When we break them into two pieces, one piece will have 50 domains in this first direction, same direction, second will have 50. As you see, when you split them into pieces, when you break them into pieces, number of domains in each piece will decrease. A number of domains determines what? Strength of the magnetic field. So the number of domains which are in the same direction determines the strength of the magnetic field. That's why when you break a magnet into two, normally this was broken, but I fixed them again. So when you break them into two, so you are going to get two weaker magnets. But when you combine the magnets, you are going to get stronger magnets. Okay? So if you break a magnet into two, yes, each piece will have two poles, N pole and S pole, and also when you break them into pieces, so because the number of domains in each piece will decrease, so the strength of the magnet will also decrease. Okay, clear?
So, teacher, you mean like the strength of the magnet is classified by the domains? The number of
yes,
domains.
classified by the number of domains which are in the same direction. Yes, you are right.
So, like the strength will decrease if you break it?
Yes, because initially in here are 1,000, give a number, random number, 1,000. When you break, each piece will have 500 and 500. Is it?
Yes.
That's why number of domains in the same direction decreases, so then strength of the magnetic field of the magnet also decreases.
Teacher, I have a point. I don't know if they ask an exam or not. By breaking the magnet, is it a physical change or something? Does they ask about it?
No. This is not what they ask. Okay, this is not for us.
Okay.
Okay, let's continue with the next part. So this man is going to bring iron filings closer to a magnetic field, magnet. See how iron filings align themselves. So this pattern is representing magnetic field lines around the magnet. So this magnet produces magnetic field lines in the space around itself. And this pattern is representing those magnetic field lines. It seems that magnetic fields are very intense at the poles, but getting weaker when you are moving away from the poles, as you see. So this is the magnetic field around the magnet. They form loops like that from one pole to another pole. So these lines are magnetic field lines. This pattern is representing magnetic field. Line seems to start from one pole and seems to finish at another pole, but in fact not. These lines continue within the magnet as well. Yani, it's from one pole to another, but continues within the magnet. From one pole to another, but continues within the magnet. So they makes loops. These magnetic field lines makes loop. Magnetic field lines of a magnet continue their path within the magnet and form closed loop. They have no ends, no beginnings. So closed loops. So because magnetic field is a vector quantity, it must be given a direction convention. Yes, magnetic field is a vector quantity as usual. Not only magnetic field, electric field, gravitational field, all they are vector quantities. All the fields are vector quantities. Magnetic field is also vector quantity. So physicists must give these fields a direction. When you look at this pattern, do you see a direction? No. Yani when you look at the pattern,
No.
there is no certain direction, but we should make some calculations. We need to give some directions. So we have to do that. Conventionally, physicists will give the direction. Conventional means according to our choice. Yani physicists will say, I am going to choose the direction of the magnetic field like that, determine like that. They will say like this. I mean, this is just a preference. I mean, according to our choices. So physicists determine the direction of magnetic field according to this sentence. Direction of the magnetic field at any point is defined as direction of the north pole of a compass at the same point. For example, I am going to locate a compass around this magnet. Compass and pole will show the direction of magnetic field at that point, like that. This red is representing the end pole of the compass. Yani in here, direction of the magnetic field will be like that. For example, in here, what is direction of magnetic field? I will put one more compass right there, and I will see that, yes, end pole of the compass will show direction of the magnetic field in here. So another point, I want to know what is the direction of the magnetic field in here. I will locate a compass right there. Direction of the end pole of the compass will represent direction of the magnetic field at that point. So you can do it for every single point around this magnet, and you can get direction of magnetic field around this magnet. And if you look at these patterns, all they are going like this. From end pole, so the line's direction is changing from end pole to S pole. Then we represent like this. Magnetic field of a magnet leaves from the end pole, enters to the S pole. From north to south pole, outside. From north to south, outside. But from south to north, inside or within the magnet, it's going to be like this. So this is the how we determine direction of magnetic field around the magnet. These magnetic fields are leaving from the end pole and entering to S pole. Leaving from the end pole, entering to S pole, have within the magnet from S pole to end pole, from S pole to end pole, outside from N to S, but within the magnet from S to